Now looking at probability, now in terms of probability, you will find different situations that arise, and one of it is an independent event. An independent event is an event which has no effect on subsequent events. If a die is rolled once or twice, then what happens on the first roll of the die does not affect what happens on the second roll of die. This is the same as tossing a coin. You toss it once, and then after that you toss it again. So if you had a head in terms of tossing the coin once, in the second toss of the coin, you're not going to necessarily get a tail. So these are called independent events, and the probability of event 1 and event 2 taking place, that you say is the probability of event 1 times the probability of event 2. Now, because they're independent. Multiplication law: a fur coin and a card is drawn from a pack of 52 cards. What is the probability that a head and an ace will result? Now, here you're looking at the probability of the head, which is half, and then the probability of ace 4 over 52, and then what is the probability that you'll get both? So it's a multiplication principle that is applying. Dependent events: a bag containing 3 blocks, red blocks, and 2 blue blocks. A block is drawn at random from the bag and it is not replaced. Now, the probability that a block is red is there are 3 red blocks and 2 blue. So that is 3/5. Then now choose a second block. Now what happens now? It means that you've got 2 red blocks and 2 blue blocks remaining. And that means the probability that this is red will be 2 out of 4. So what happened in the first event as the first activity as impacted on the second, and the probability, and it will continue like this, and these are called dependent events. You can do the next problem on your own, and then you're looking at mutually exclusive events. Now mutually exclusive events, now if 2 events could not happen at the same time, they are to be mutually exclusive. It is not possible to obtain a 3 and a 4 when you roll a die once. But you could get a 3 or a 4. They are mutually exclusive, 3 and a 4. So the probability of getting a 3 is 1/6. Probability of getting a 4 is 1/6. The probability of getting a 3 or a 4 is the probability of event 1 plus the probability of event 2. So in other words, 1/6 is the probability of getting a 3, 1/6 the probability of getting a 4. So what is the probability of getting either or, which when you add you get 1/3. So those are called mutually exclusive events. Non-mutually exclusive events. What is the probability of drawing a jack and drawing a diamond? These are not mutually exclusive events. Why? The probability of drawing a jack or diamond will actually be a situation like this. Probability of jack or diamond. Now is the probability of us drawing a jack. Now that is 4 over 52. Then the probability of drawing a diamond there are 13 diamonds. That's 13 over 52. Now, but there is one which is the jack of diamond. So it's included in that and included here. So these are non-mutually exclusive. You can see the reason for that. So we say the probability of drawing a jack or diamond is the probability of a jack plus the probability of diamond minus the probability that you got a jack which is also a diamond, and that is 4 over 52 plus 13 over 52 minus 1 over 52, and that will give you your answer that you require. Non-mutually exclusive events. And then finally the probability tree. And I'm going to just deviate slightly from this problem here and say that we tossing, let's assume we are tossing a coin, right? And then we want to know we want to toss a coin twice, and then we will ask the question. So when you toss a coin, you've got two outcomes. One is head and the other is a tail. So probability of getting a head is half, probability of a tail is another half. Now that's on your first. Second time when you toss a coin, now because remember they're independent, so you can get a head or a tail, and then that's half and that's half as well. So here you can also get a head or a tail. That's half and this is half. So if I ask you what is the probability of, now we're going to use the multiplication principle here as well. What is the probability of getting a head followed by a head? Or two heads? So that's the probability of getting the head in the first one times the probability of getting a head again. So that's half times half, which is a quarter. Probability of getting a head followed by a tail, head followed by a tail, then it means you got half times half. Head and tail, they're not telling you in which order, so you can get head or tail and head. So head and tail will be a quarter, tail and head will be a quarter, so you've got to add those results which we just discussed. So that's the advantage of doing a probability tree. But your limitations, there are plenty of limitations. Therefore when you do the binomial expansion, you'll find how effective it is. You can toss a coin 5 times and you can ask the question, what is the probability of getting 4 heads? And because you've got just 2 outcomes, you can use the binomial expansion for that. Right, now this problem here is on probability. A bank employs 2 managers of a certain branch. The head office sent a coded message to the branch. The probability that manager A can understand the message is 0.25. Probability that manager B can understand the message is 0.67. Manager A works independently of manager B. We are now saying C1.1. What is the probability that manager A and manager B can understand the message? The probability that manager A understands the message is 0.25, and the probability that manager B can understand the message is 0.67. Now we are now asking what is the probability that both the managers would understand the message. So it is the probability of A times the probability of B. And that's 0.25 times 0.67, giving us 0.1675. 1.2 says, calculate the probability that at least one of them will understand the message. Now, since there are only two people, what we can say is, let us say that A does not understand the message and B doesn't understand the message. Now, probability that none of them can understand the message, probability that A that will not understand the message is 0.75 times the probability that B will not understand it is 0.33. And you multiply that out, and then you want to find out the probability that at least one will understand the message. At least one will understand the message. One understand the message is equal to 1 minus 0.75 times 0.33, and that would give you the answer 0.7525. This is number 5 on page 93, and here we are saying that 3 friends take part in the Two Oceans Marathon. The probability of each one of them completing the marathon is given. Probability that A would complete the marathon 0.8, B 0.5, C 0.3. What is the probability that at least two of them will complete the marathon? So probability of at least 2 completing the marathon, 2 completing is equal to the probability that A will complete, B will complete, and C will not complete, plus the probability of A completing, C completing, and B not completing, plus the probability of B completing, C completing, and A not completing, plus the probability of A completing, B completing, and C completing. And that should take care of the problem, which means that probability of A completing 0.8 times 0.4 times 0.3, because the C would not have completed, plus probability of A 0.8 times 0.7 times 0.6 not completing, plus B completing 0.4 times C completing 0.7, A not completing 0.2, plus all completing 0.8 times 0.4 times 0.7. And that will give us an answer of 0.712. Now 5.2 says, what is the probability of none of them completing the marathon? Probability of none of them completing the marathon is probability of A not completing, B not completing, and C not completing, which means that 0.2 times, and B not completing will be 0.6, and C not completing will be 0.3, and the answer is 0.036. And that takes care of that problem. This problem is number 3.4 on page 95. Now, I did say that factorial, 3 factorial is 3 times 2 times 1. Now, in the previous problem as well, we can say that we can talk about n permutation R, and n permutation R is the number of permutations of n distinct objects taken R at a time. So if you've got a number of ways, and that is equal to the number of ways n permutation R, and if you expand that, you will get n factorial over n minus R factorial. And we're going to use that in future as well. Now, so if you take the case of 12 runners and determine how many ways can the runners finish in first, second and third place, you will find that 12 runners can finish in first place, any one of 12. Any one of 11 runners can finish second, any one of 10 runners can finish. So the number of ways, so you've got 12 permutation 3. So that was 12 permutation 3. Let's assume that. Now 12 permutation 3 is 12 factorial over 12 minus over 9 factorial, because you're excluding all the others. So it will be 12 times 11 times 10. That is the basic answer from this, which is actually, we said 12 times 11 times 10. And if you look at your calculator, makes provision for that, where you can actually now go on and say, in terms of your calculator, we're looking at 12, and then you can go on to your shift and NPR 3, and you will get your answer 1320. Now, let's take this problems here. 3.4.1 says, in how many ways can the group sit together? The 5 people, they went to the cinema and they can sit at any point. So the number of ways, the 5 people, it's basically NPR 5 permutation 5. And your answer there is 120. Second question says, in how many ways can the group sit together if 2 people must sit next to each other? Now this is a problem. So what we do, we consider the 2 people like one person. So if you consider the 2 people like one person, then you're looking at 4 people taking 4 seats. So the number of ways is 4 permutation 4. So because we're regarding the 2 people as one. But then, you remember, if the 2 people are sitting next to each other as A and B, they could also sit as B and A. So you're going to multiply this by 2, and then when you do that, you 4 permutation 4, and you remember that 0 factorial is 1, and 1 factorial is also 1, and your answer here is 48. Then if you take 3.4.2, the number of ways, you will find 3.4.2 is talking about in how many ways can the group sit together if 2 people refuse to sit next to each other. Now these 2 people are sitting next to each other. There are 48 ways in which they can sit next to each other, but if they refuse to sit next to each other, then it means that the 120 minus 48 is 72 ways in which they will not sit next to each other. This next topic is on counting methods, and counting methods starts from page 94. Now, if you look at the first one, it talks about repetition or no repetition. In a beauty competition, there are 12 contestants. 3 prizes are awarded for the categories Miss Photogenic, Miss Personality, and Miss Model. In how many ways can the prizes be awarded? The first prize can be awarded in 12 ways. The second prize also in 12 ways, because the first one won qualifies. And the third prize can also be awarded in 12 ways. So therefore, the total number of ways is M1 times M2 times M3, which is 12 times 12 times 12, 1728, and that is repetition for us. So the number of ways is M to the N. Now, this is a fundamental counting principle. Then if you take a social club organized 4 events for 10 runners, each event carried a prize and every member could participate in all 4 events. In how many ways can it be awarded? It's the same principle as above. Now, if you look at the next one, which is called permutation, in how many different ways can 3 people be assigned to 3 different jobs? Now, suppose 3 people are A, B, and C, and we have job 1, job 2, job 3. Now, if you look at job 1, if you look at all possibilities, there's 6 possibilities. Let's assume that all 3 go to job 1. Now, the number of ways of assigning job 1 is 3 ways. Either A, B, or C will get the job. Now, assuming one of them got the job, and then it will leave you 2 people going to job 2. Number of ways of assigning the 2 people to job 2 will be 2. This will leave us with 2 people. And assuming one gets the job, then the number of ways of assigning job 3 will actually be left to 1, and this person will just by default get the job. So the total number of ways of assigning the 3 jobs to 3 people will be 3 times 2 times 1, and that will give you 6. Now you'll notice that order is important here, and there are no repetitions. And so and then 3 times 2 times 1 is 3 factorial, which is equal to 6. And 3.5 on page 95, a bead maker makes 5 beads at a time. There are 3 indistinguishable red beads, 1 blue and 1 white. How many arrangements are there? Now you can actually try this out. Remember, the reds are indistinguishable. So, what it really means is if I got red, and I got a blue, and I got a white, and I got red. Now these reds are indistinguishable. It means you can't say let's move this red to 5th position. No, they're indistinguishable. So the point here now is how many arrangements. So number of arrangements is equal to, the number of arrangements is equal to, now let's assume we have the total number, which is n, so it will be called n factorial over a factorial, b factorial, and c factorial. The a, b, and c are the n is actually divided into those 3. So we are saying 5 factorial divided by a factorial is 3. Let's say the reds were there. So there's 3 factorial, 1 factorial times 1 factorial. 1 factorial is 1 times 1 is 1. So 5 factorial divided by 3 factorial, which can be done as well. and that gives you 20. Now what happens if there were 3 red and 2 white? So if the 3 red and 2 white, then you will get 5 factorial. So the number of arrangements will be 5 factorial over 3 factorial times 2 factorial. And that will give you the answer 10.